Now we have seen how the measurements of gravity is made either by absolute gravity measurements, that is known as what is known as usually the popular gravimeter to measure the absolute G value is weight dropping method, right. After that we had seen relative measurements, right, relative G value. Relative G value can be determined by both unstable as well as stable gravimeters. So, now we have learned how the gravimeter is used to determine either the absolute gravity value or the relative gravity value. Relative gravity value can be determined by both stable gravimeter as well as unstable gravimeter. Now, let us see, we can use any type of gravimeter sold in the market according to our wish and convenience. Now, we have got the data, but is the data which we have got is really correct? How can we make sure that the data which we have obtained using the gravimeter is perfect? That can be assessed only by calibration of the gravimeters, which means before carrying out the survey, we have to make sure the gravimeter which I am going to deploy today for measurements is capable of measuring the values perfectly. So, this can be achieved only by calibration of the gravimeters, right. So, how calibration can be done? So, what is calibration? For example, so I am wearing a watch, I do not know whether the watch shows the precise time. In order to make the watch to show the precise time, the watch undergoes a process of calibration at the manufacturer's of laboratory, isn't it? In the same manner, here we may have a very sophisticated expensive gravimeter with us, but before going to the field, we need to check and calibrate the gravimeter, our own gravimeter. How it is done? This is done by comparing the reading which we have obtained, right. It can be from any method, maybe by weight dropping method, or by a popular stable gravimeter, or by a popular unstable gravimeter. So, what we do, the reading which we have obtained can be compared with the previous readings of the same station, right. Present and the previous reading may be from the same station, right. So, check, oh, today you have measured the value here and tomorrow you measured the gravity value there, whether the instrument shows the same value or not, right. There are also other reasons for the change in the gravity with respect to time, we are going to see that, right, just to make sure the instrument is reasonably fine, right. However, precise calibration can be obtained by comparing the values of number of reference stations, right. You may have number of reference stations around you, especially in meteorological departments, right, especially in India, IMD, in many stations they have the gravity readings measured and also published at different times. So, we can go and verify whether our gravimeter shows the same value by taking it to the gravity stations, right. Or we can also make use of the values published at the pendulum stations, right. Similar to the international gravity station, so we can compare our value with the pendulum station values. If the instrument's value is the same as that of the pendulum station, that means we take our equipment to the international gravity station, over there we deploy and measure the gravity value, right, either relative or absolute. If you want to check the relative measurements, you need two stations. If you have absolute gravimeter, your gravimeter can be calibrated by taking it to the one station, but it is always precision is obtained by checking with a number of stations. It is at least 2 or 3 stations will be better. Okay. Then the other way of checking is taking the measurement at different heights, right. You do not have a nearby station, but if you have a relative gravimeter or absolute gravimeter, you can determine whether your instrument shows this much of a difference for height. That means this is, let us say, 0 level. Here you have made the measurement of gravity. Then you are lifting the instrument to +1 meter. When you lift the instrument to +1 meter, the gravity value should decrease by minus 0.3086 milligauss, right. If you take it to 2 meters, then 2 times of this should be the reduction in the value, right. So, this is how we can check our gravimeter. Then lastly, some manufacturers provide a mechanism of calibration, a method of calibration by tilting the gravimeters. Gravimeters are kept essentially vertical to make the precise G value. Some manufacturers also give a provision. Suppose if you tilt the gravimeter by 2 degrees, the gravity value should decrease by this much milligauss. If you tilt it by 4 degrees, 6 degrees, 8 degrees, this will be the corresponding decline in the gravity value, right. So, we can use this method also to calibrate the gravimeter. That means what we have seen? We have seen number of methods of calibration. Precisely, we can say 3 methods. These 2 are more or less the same. So, one is taking the instrument to the reference station, 2 is taking measurement from different heights, method 3 is tilting the gravimeter. Now, we know when you tilt the gravimeter, so much should be the reduction in gravity given by the manufacturer. If the same reduction if you get, we are happy. Similarly, here in second method, you are increasing the height of measurement. When you increase the height by 1 meter, precisely the gravity value shown by the gravimeter is reduced by 0.3086, then instrument is functioning well. Let us take the first method. I am taking the my relative gravimeter to 2 stations. This is station number 1, station number 2. They are all international gravity stations, right. International gravity stations, International Gravity Station 1, International Gravity Station 2, right, or in other words we popularly call them as pendulum stations. I keep the instrument here, right, and then take the instrument here. This is a relative gravimeter. So, I am able to determine the difference between station 1 and station 2. Let us assume it is 0.05 milligauss. This is the difference I got. At these 2 stations, already we know the gravity value because it is a pendulum or international gravity station, right. So, we know the difference between the 2 stations, the values are already published. If it is 0.05, we are happy, right. Suppose whatever method you have used, the value which we are getting is not as expected, then we need to calibrate the instrument. That means manufacturers have provided a way to change the reading by this process is known as calibration. For example, I kept the instrument here, I shifted the instrument here 1 meter, the reduction in gravity should be 0.3086, but the gravity has decreased by 0.4 milligauss. Okay. Then you use the calibration screw, bring the value to 0.3086. This process is known as calibration. After having done that, recheck. Couple of times you recheck to make sure the instrument is working well. This is something similar to in some weighing machines or bathroom scale which we use at our home. They would have provided a mechanism to bring the value to 0. Sometimes it may show plus 500 grams or minus 500 grams. There is a provision. Similarly, in our old clocks, there is a provision to calibrate the clocks. Exactly the same we will do for the gravimeter. After having completed the process of calibration, now we are sure the gravimeter is working well. When will we do the calibration? Calibration is always done just before commencing our work. Preferably, if you had planned to carry out the gravity survey today at 7 o'clock, start your calibration process before and check whether everything goes well. Or if previous day we can complete the calibration and next day before taking the instrument to the field, make sure it shows it is properly calibrated by doing these checks. Okay, then we are very sure we are not going to waste our time, right? After completing the survey, if the readings are not proper, then we waste the entire day's work, isn't it? So, better to calibrate the work previous day and also double check just before the commencement of the work. Now, our instrument is calibrated. What next? Next is we should also understand the fact I made a mention, the value of gravity also changes with respect to time. Isn't why? This is what is known as drift in the readings. What is drift? Drift is change in the gravity values or gravimeter readings with respect to time. Continuous variation in gravity with respect to time at the same station. What are the reasons? Two principal reasons. One is the instrument error. Number 2 is beyond the instrument's control, right? That is the location of the sun and moon. We have seen already the Newton's law of gravitation. Mass 1, mass 2 are attracted by each other. We had seen previously, we consider the mass of the earth as m1 and the small mass which we keep at the surface is m2. These two are attracted by each other, right? In the same way, this is earth and we have sun here. The sun and the earth is also attracted towards each other, right? This will affect the gravity value which we are going to measure, right? So, that is the second reason. First reason is, though the instrument manufacturers manufacture the instruments with the greatest care, right? Most of the gravimeters are highly insulated, right? Also, there are temperature compensators in gravimeters. We didn't go into greater depth, right? Gravimeters can be kept at a specific temperature, right? There are, with the help of a battery backup, right? Suppose the anticipated maximum temperature which you expect today or during the day of your investigation is 38 degrees, the instrument can be kept at 40 degrees. That means, inner part of the instrument can be kept at 40 degrees throughout the day. Why? Because change in the temperature may make some changes in the components of the instruments, though they take lot of care, right? The instruments are made preferably with some natural minerals, so that there is expansion and contraction is very much minimized, but in spite of all the care, there can be some minor changes, especially with regard to the spring type gravimeters. Most of the gravimeter which we use are spring based, spring gravimeter, that is unstable or stable gravimeters. Weight dropping is not dependent on spring, whereas all the other gravimeters are spring based. So, minor change in the length of the spring due to the atmospheric temperature variation will cause the readings to change. So, if you leave your gravimeter at the same station throughout the day, the values will change. That is what is known as drift of the instrument, which has to be measured by us. Okay, why we may have to correct our readings. So, this is what is known as drift in the equipment. So, here is a picture of the drift curve. What is drift curve? Drift curve is showing us the value of the gravity, either absolute or relative. Here we are seeing the relative gravity, how it varies with respect to time. So, here is the time axis, and here is the ocean tide. The tide level varies up and down with respect to time. In the same way, the earth's gravity also is going to vary. Why you have tidal variation? Because of the interplanetary pull between the earth and the other nearby planets. So, the instrument also will be subjected to this earth and ocean tide variations, right. Hence, in order to obtain this, we deploy the instrument at one place and we measure. This is the time axis and here is the delta G value, maybe in milligauss, right. Let us say this is 0, this is plus 1, this is minus 1, right, and here is the time 6 a.m., this is 6 p.m. So, we keep measuring the values. Let us say 6 a.m. we have kept it as 0, our reference. With reference to that, it will not remain as 0 continuously, but slowly the value may increase and then it may come down also. This is what is known as a drift curve. So, how did we obtain this? We have kept the instrument at the same station from morning to evening. Otherwise, we have gone there at intermittent intervals 6, 6:30, 7 a.m., 7:30, every half an hour or approximately for every half an hour or 25 to 35 minutes we have been there. We have noted the time as well as the gravity value, relative G value, time and delta G value, right. So, delta G is with reference to a common time. We may assume 12 a.m. as our reference time. With reference to that, how the value varied at different locations, that is what is known as delta G, right. 6 a.m. 0, 6:30 a.m. it is plus 0.1 milligauss, this is in milligauss, this is in time. 7 a.m. same value, right. 7:30 plus 0.15. Next one we could not go at 8, but we have gone at 8:05 a.m. What is the value? 0.151. This is how we note down the values. Plot of time versus delta G is known as drift curve. Okay. So, drift is monitored by repeating the reading at the same station at different times of the day. This interval is left to you, right. Preferable to go every 15 minutes or half an hour, depending upon the site conditions and the logistic facility. You can decide the time interval and prepare what is known as drift curve as I have plotted, right. Drift values are typically about less than 10 gravity unit per hour. If you get beyond this, I think no point in continuing your work because there is some problem with the instrument. Normally every hour the gravity value can change only up to about 5 gravity unit or 3 gravity unit, then it is fine. Most of the drift is due to the external effects, not due to the error in the instrument. Okay. So, this is how we prepare the drift curve. Instrument drift correction has to be estimated from the drift curve. Why we are preparing the drift curve? We need to correct all the values which we have obtained from our steady site in such a way we have made the measurements at the same time. How do you achieve that? You have the drift curve. Imagine this is 12 noon, right? At 12 noon or 12:05, at 12:05 hours or PM, you were at one station. This is your steady site, this is your gravity station. Here you have made the value at 12:05 PM, right. Now, we decided to convert all the reading as if they were taken at 6 AM, because 6 AM we are going to fix it as our reference time. So, you check this diagram at 12:05 you are somewhere here, the value you have measured is much higher than 6 AM value, isn't it? So, this is at the same station. Here this is plus 0.75 milligauss. The difference between 6 AM and 12:05. That means at the unknown station, the value which you have measured some G value, that G value is likely to be higher by 0.75. So, subtract 0.75 from the value you have got. This is what is known as drift correction, right. In order to obtain drift correction, we prepare this drift curve. Is that clear? That means our aim is to get rid of the drift. Okay. How we achieve that? We achieve that by preparing a drift curve. So, when you are doing a survey in the field, you choose one station preferably at the middle of your site with a easy access as your base station. Visit the base station every 20 or 30 minutes or at least every half an hour, right. Every half an hour or 1 hour you would have made the measurement of gravity, using which you will prepare the drift curve. This curve is prepared based on that. Okay. So, this is how we prepare the drift curve, and we understand about the drift in the equipment, or not equipment, drift, due to these two reasons. One is the equipment reason, another one is the location of other planets around us, right. Now, we have made the drift curve. Then, how are we going to carry out the survey in the field? First and foremost, as we have seen previously, latitude and elevation has to be precisely measured. Let us say this is the steady site and these are the gravity stations. We should know the station's latitude with an accuracy of plus or minus 10 meters. Similarly, elevation accuracy should be of the order of few centimeters. Why? Because we know for every meter change in the elevation, the gravity value is going to vary by 0.3086 milligauss. We need to reduce this value, or we need to correct for the elevation. So, we need to know the precise latitude as well as elevation of our gravity stations. How are we going to do the survey? Usually, gravity survey is made on grid pattern, right. That means, if this is your steady site, we divide the site into number of grids. right, maybe like this, but I am not drawing the lines, I am just putting the, I am drawing the dots, right. At all these dots we are going to make the measurement of the gravity, but the question is, what is the distance between the dots or our gravity station? That depend on the aim of the survey. If you are searching for oil reserve, then distance can be few kilometers, right. Or if you are searching for a artifact within a small area, then you have to keep the stations at much closer interval. So, it depends on, usually we carry out gravity survey by grid pattern, but the distance between the stations depend on the aim of the survey. And after deciding the distances, next is carrying out the leveling and surveying, that is what is determining the latitude and elevation. As I have been telling you today, it is very easy with the advent of differential global positioning system. We are able to get the accuracy in few centimeters, right. The level accuracy is in centimeters, then you can latitudinal accuracy is much better, even less than 1 meter. So, accurate we are able to get. So, this was very difficult. In fact, in olden days 25-30 years ago, gravity survey will take more time because we spend most of our time for surveying. Actual gravity measurements using gravimeter is only 1 minute, not more than that, because modern day gravimeters, as I told you, even approximately if you level it, that is sufficient. Rest of it, the instrument automatically carries out leveling, or it is able to correct the readings for inaccuracy in our leveling. So much advanced. So, the time spent by us for surveying was much higher those days, but today, thanks to differential global positioning system, we are also able to quickly determine the latitude and elevation with the highest accuracy using DGPS. After that, we go to the site and deploy the gravimeter and make the measurement of gravity, either absolute or relative. Any of the gravimeter which we have seen can be put into use. This takes only few minutes, right, whereas in resistivity survey or in seismic deployment arrangement takes most of the time, most of our time. Here it is very simple, take the gravimeter, keep it, take the measurement, level it, take the measurement, maximum it will take 1 or 2 minutes, that is it, go to the next station. Now, we have the readings with us. However, readings have to be corrected. The data which we have, that gravity data which we have has to be corrected. For what? They have to be corrected for several things. One is latitude. That means we know already, we have seen already, Earth's gravity varies from equator to the pole, right. Equator to the pole, Earth's gravity varies. At the equator, it is less gravity here. Here it is more g, less g. Why? Because radius is 21 kilometers more at the equator. Equator to the center of the earth, the radius is 21 kilometer more than this distance. Okay. So, due to which gravity value is lesser. So, when you suppose if this is your steady site and this is north, some stations are here, some stations are here. Imagine this is in the northern hemisphere, our steady site is in north. If it is in northern hemisphere, then the values which you are measuring here is expected to be more than this station, because this is, let us say this is station number 21, This is station number 8. Station number 8 is located slightly closer to the center of the earth. So, the mass in your gravimeter is attracted much more at station number 8 than station number 21. We need to correct for this. That is what is referred as latitude correction. Similarly, elevation, terrain, diurnal we had seen under drift. All these corrections have to be given. After you carry out all this correction, that means after you have corrected the readings, then the data is ready for interpretation, right. That means we have made measurements, all these measurements are showing different values of G. The reasons for different values in G value is due to large scale variation, that is, earth is not a sphere, due to latitude, due to time, due to diurnal. That is why we apply all these corrections. After applying all the corrections, the data has been now reduced. That means we got rid of all the impacts on the G value, right. For example, latitude, elevation, all these effects we have removed, and also time wise variation, everything we have removed. Now we have got the reduced data. In other words, simply I can say cleaned data is with us, using which we can prepare the anomaly maps. This is what is known as interpretation. We are into interpretation, right. And then we can determine size and shape of the bodies, right. That means this is quantitative method of investigation, right. And the greatest advantage is gravity methods can be operated on land as well as from air as well as ship, right. From everywhere we can land, or from sky, or from air, or from water, we can do the measurements of gravity survey, right. So, in today's lecture, we have started with what is gravimeters, how gravimeters are measuring the earth's gravity. One set of gravimeters are known as absolute gravimeters, and the other set of gravimeters are relative gravimeters. The popular absolute gravimeter is based on weight dropping method. Then we had a look into relative gravimeters, which are classified as stable and unstable. In stable, extension of the length of the spring is measured. In unstable, the mass is restored to the original position by adjusting the micrometer screw. So, micrometer screw helps us to know the difference in gravity between the two stations, right. So, we had seen different gravimeters very briefly. Then we had a look into how gravimeters are calibrated. Then after calibration, how the instruments are deployed to carry out the survey in the field. This is what we have seen in this particular slide. We will continue with the how corrections are going to be applied in the next lecture. Thank you very much.